Hello everyone. In this video, we shall discuss about polynomial functions and some of its basic properties. So what is a polynomial function? A polynomial function of degree n is a function of the form f of x equals a sub n times x raised to n plus a sub n minus 1 times x raised to n minus 1 plus up to a sub 1x plus a sub 0, where the coefficients a sub n, a sub 1, up to a sub 0 are real numbers, and n, which is the degree of the polynomial, is a non-negative integer. The number a sub n is restricted to be not equal to 0 because if a sub n is 0, a sub n times x raised to n will become 0, and the polynomial function degree will be reduced to n minus 1. So that's why a sub n should not be equal to 0. Now this a sub n is the coefficient of the variable with the highest power, and this is called the leading coefficient. So here are some examples of polynomial functions. First, we have f of x equals 3 times x to the fourth minus 2 times x cubed plus 5 times x squared minus 7x plus 9. And since the highest exponent of the polynomial function is 4, this is a polynomial function of degree 4. Second, f of x equals x squared plus x minus 6 is also a polynomial function, and this is of degree 2. This is specially called the quadratic function, which we learned in the previous video. Third, we have f of x is equal to 4 times x minus 7, and this is a polynomial function of degree 1. So polynomial functions of degree 1 are also called linear functions. And then fourth, we have f of x equals 8. So since this is a constant, this is a polynomial function of degree 0. So polynomial functions of degree 0 are also called the constant functions. So these three functions, constant, linear, and quadratic, were discussed in the previous lecture videos. But in this particular discussion, we will be focusing only on polynomial functions having degree that is at least 3. Okay, so these are the graphs of the polynomial function. So we know that if the polynomial function is of degree 2, it is a quadratic function, and we already know that its graph is a parabola that opens upward or downward. But if we have polynomial functions of degree 3 or higher, then the graph has different variations. So in this column, this is a graph of a polynomial function of degree 3, and it shows that this graph doesn't have any bumps, okay, but it has one flex point. Now for the second example here of a polynomial function of degree 3, this graph has 2 bumps, and for polynomial functions of degree 4, we have graphs with 1 flattened bump and graphs wherein we have 3 bumps. So the graphs of the polynomial function depends on its degree and depends on the intervals where the function would increase or decrease. So for this discussion, we will not focus on sketching the graph of the polynomial functions, but we want to identify the properties of these polynomial functions. So the properties of polynomial functions, so its domain is always the set of all real numbers. So it's written as the interval from negative infinity up to positive infinity. However, its range would depend on the degree of the function and would depend on the bumps in the graph. So in order to determine the exact range of the polynomial function, it is better to inspect the graph of the function. Now, graphing of polynomial functions would require some concepts from higher mathematics like calculus. But since we're not yet in that course or level, then we will just consider graphs of polynomial functions, and we will not sketch the graphs of polynomial functions. Now, the x-intercepts are obtained by solving the equation f of x equals 0, just like the previous functions that we have studied already. Now, the y-intercept is obtained by evaluating the function at x equals 0, or we evaluate f of 0. So for example, let's consider the function x cubed plus x squared minus 4x minus 4. This is a polynomial function of degree 3. So let's determine the intercepts of this function. So for the y-intercept, we shall solve for f of 0. Now, of course, f of 0 means that we will replace every occurrence of x by 0. So this means that the first three terms of this function will become 0, and then the function value of x equals 0 is negative 4. Now for the x-intercept, we shall equate the expression to 0, and then we solve for the values of x. Now if we have some polynomial equations of degree 3 or higher, it would require some concepts from uh, finding the factor or remainder theorem. But in this discussion, you will focus only on examples wherein the polynomial functions are factorable. So in this case, since this expression at the left side has four terms, we can try factoring this by grouping. So we can try grouping the first two terms, and then we group the last two terms. But since the last two terms is preceded by a negative sign, so when we group them, we are going to change their sign. So this negative 4x here will become positive inside the parentheses, and this negative 4 here will become positive inside the parentheses. So we get the following equation. So now that we have grouped already the appropriate terms, we can find a common factor for each group. So for the first group, x cubed plus x squared, we can factor out x squared. And then for the second group, we can factor out 4. So we can write this as x squared times the quantity of x plus 1. And then since 4 here is factored out, we have minus 4 times the quantity of x plus 1 equals 0. Now this resulting equation, if we observe, has a common factor, which is the quantity of x plus 1. So we can factor it as x plus 1 times x squared minus 4 equals 0. And then x squared minus 4 can still be factored as x plus 2 times x minus 2. So equating all these linear factors to 0 and solving for x, we will get x equals negative 1, x equals negative 2, and x is equal to positive 2. So therefore, the x-intercepts are negative 1 comma 0, negative 2 comma 0, and positive 2 comma 0. While for the y-intercept, it is the point 0 comma 4. Now shown in the next slide is the graph of the function. I obtained the graph from the GeoGebra online. So as you can see here, this is negative 2 comma 0, negative 1 comma 0, and positive 2 comma 0, which are the x-intercepts. And this is 0 comma negative 4, which is the y-intercept. So since we're not supposed to sketch the graph of the function, let's just consider the domain and range from this given graph from GeoGebra. So since the graph here extends indefinitely in both left side and right side, its domain will be the set of all real numbers. And then if you notice, the graph extends indefinitely upward and extends indefinitely downward. So that means the range is also the set of real numbers. Okay, next example, let's now consider f of x equals x to the fourth minus 10x squared plus 9, and determine the intercept. So just like in the previous example, for the y-intercept, we will evaluate f of 0. So that will be 0 to the fourth minus 10 times 0 square plus 9. And then 0 to the fourth minus 10 times 0 square will just be 0. So therefore, the function value of 0 is 9. So that means the y-intercept is the point 0, comma 9. Now for the x-intercept, we will equate x to the fourth minus 10x squared plus 9 to 0. And then we factor the expression here. So this expression is in quadratic form, or we can factor it as x squared minus 1 times x squared minus 9. It's because x to the fourth can be factored as x squared times x squared. Positive 9 can be factored as negative 1 times negative 9. And then if we check the outer product and the inner product, that's going to be 9x squared minus x squared, which is negative 10x squared, which matches the middle term here. So these are the correct factors. Now, x squared minus 1 is a difference of two squares. X squared minus 9 is also a difference of two squares. So these two can still be factored as x plus 1 times x minus 1. That's for x squared minus 1. And x squared minus 9 can be factored as x plus 3 times x minus 3. So equating all these linear factors to 0 and solving for x, we will get negative 1, positive 1, negative 3, and positive 3. So therefore, the x-intercepts are the points negative 1, comma 0, positive 1, comma 0, negative 3, comma 0, and positive 3, comma 0. So here is the graph generated from GeoGebra. So the x-intercepts are negative 3, comma 0, negative 1, comma 0, positive 1, comma 0, and positive 3, comma 0. And then the y-intercept is 0, comma 9. So since the graph is already given from GeoGebra, let's determine the domain and range of this function. So since the graph extends indefinitely going to the left and rightwards, then the domain is the set of all real numbers. But in the range, when the graph only extends indefinitely upward, so it has a bound below, so which means that the graph starts at y equals negative 16, and then it extends going upward. So that means the range is the set of all y such that y is greater than or equal to negative 16. So in interval notation, that can be written as square brackets, negative 16, comma, positive infinity, close parentheses. Okay, now we have another example. So let's consider this time f of x is equal to negative x cubed plus 4x. And let's determine the intercepts of this function. So for the y-intercept, again, we write it as f of 0 is equal to negative of 0 cubed plus 4 times 0, which is equal to 0. So this means that the y-intercept is the point 0, comma 0, or the origin. Now for the x-intercept, we will equate negative x cubed plus 4x to 0, and then we factor out x. So x, or we can factor out negative x, and then we get negative x times x squared, and then minus 4 is equal to 0. So which means that x squared minus 4 can still be factored as x plus 2 times x minus 2. Now equating all these factors to 0 and solving for x, we will get x equals 0, x equals negative 2, and x is equal to positive 2. So therefore the intercepts or the x-intercepts are 0, comma 0, negative 2, comma 0, and positive 2, comma 0. So the graph of this function is shown in the next slide. So here are the x-intercepts, negative 2 comma 0, 0 comma 0, and positive 2 comma 0. And the origin 0 comma 0 also serves as the y-intercept. Now, since the graph extends indefinitely leftwards, and extends indefinitely rightwards, then its domain will be the set of all real numbers. And since the graph extends indefinitely upwards and extends indefinitely downwards, then its range will also be the set of all real numbers. So this ends our video about the basic properties of polynomial functions. So I hope that you learned something about it. And please don't forget to subscribe to my channel. Thank you for listening.